Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through integral domains. So an integral domain is a special type of commutative ring that has no non-zero zero divisors. So what do we mean by that? Well, let's look at the product A times B, where A and B are elements of the ring. So remember, we learned in a previous video that A was a zero divisor if A times B is equal to 0, but B does not equal 0. That's what a zero divisor actually is, a number that you can multiply by something non-zero to get 0. So in an integral domain, the only zero divisor is 0. That means if A times B is equal to 0 and B doesn't equal 0, that means that A must equal 0. So in an integral domain, you cannot multiply together two elements of the ring, of the integral domain, to get 0. If you multiply two non-zero numbers together, the answer you get will always be non-zero. So just before I give you some examples, I want to note here that an integral domain just has to be a commutative ring. It does not have to be finite. So remember, we learned in a previous video that in a finite ring, every element is either a unit or a zero divisor, but not both. But since the ring does not have to be finite, in an integral domain, not all elements are units. There are some elements that are not units and not zero divisors. This is if the ring is infinite. So for example, Z is an integral domain. The set of integers, the ring of integers, is an integral domain because we know that if we multiply together two non-zero numbers like 4 and 3, we will not get an answer of 0. But that doesn't mean, because Z has no non-zero zero divisors, that doesn't mean that all the elements of Z are units. In fact, in Z, the only units are +1 and -1. Okay, so I just wanted to make that point. So Z is an example of an integral domain. So too are the rational numbers. You can't multiply together two rational numbers that are non-zero and get 0. The real numbers are. All these are examples of integral domains. So what's an example of a ring that is not an integral domain? Well, I'll give you the example, one that we've seen before, Z8, the set of integers modulo 8. So this is not an integral domain because it has non-zero zero divisors. So what I mean by that is in Z8, 4 times 2 is obviously 8. But that is equivalent to 0 in the integers modulo 8. So in Z8, 4 is a zero divisor, 2 is a zero divisor, because you can multiply each of them by something non-zero to get 0. We've multiplied two non-zero numbers and got an answer of 0. So this means that the set of integers modulo 8, though it is a commutative ring, it is not an integral domain because it does have non-zero zero divisors. Something like Z7, though, the integers modulo 7, that is an integral domain because you can't multiply together any two non-zero numbers in modulo 7 and get 0. So as it stands now, we haven't yet uncovered which set of integers modulo n is an integral domain and which sets are not, but we will do that as an exercise. So why is an integral domain important? Why do we need to know about these things? Well, it turns out that in an integral domain, you can apply what is called the cancellation law. It essentially allows you to divide. We've talked about rings. They have addition and sort of by extension of that, subtraction as well as multiplication defined in them, but they don't necessarily have division defined for them. We need the cancellation law to allow that to happen. So the cancellation law says that if R, the ring, is an integral domain, that's what I mean by ID, and let's say A, B, and C are all elements of R. So then, if I have A times B is equal to A times C, and A is not equal to 0, then what I can do with the cancellation law is cancel the A's from both sides. Essentially, I'm dividing each side by A. And then I'm left with B is equal to C. So I can only perform such a division in an integral domain. So I wouldn't be able to do something like that in the integers modulo 8. So it turns out that the two conditions we've gone through are equivalent. So a ring having no non-zero zero divisors means that you can apply the cancellation law in that ring. If you can apply the cancellation law, as I've said over here, then the ring will have no non-zero zero divisors. So I'm going to leave the proof as an exercise, but that's why integral domains are very important. So note, the reason we went with this definition up the top regarding no non-zero zero divisors is that is usually much easier to check than to see whether all the elements in the ring can satisfy the cancellation law. Alright, I hope you've enjoyed this video. This has been the luckiest maths teacher in the world. Have a great day.